The National Weather Service says tsunamis are not expected for the U.S. West Coast or for British Columbia.
Fire flared up on Monday evening, burning on both sides. It quickly forced the closure of the highway to Bamfield.
Under the vast Pacific, the Cascadia Subduction Zone stretches from northern Vancouver Island down to northern California, a profound and silent threat capable of generating earthquakes well over magnitude 9.0 and tsunamis towering nearly 100 feet. It is a geologic titan composed of the Juan de Fuca, Gorda, and Explorer oceanic plates pressing downward beneath the continental North American plate, their slow descent measuring about 40 millimeters per year. Most of the time, the subduction zone lies dormant, its slumber belying the imminent power it holds. But at deeper depths, slow slip events and episodic tremor occur, generating faint rumblings that the ground doesn't feel, but scientists track. Before we start, smash the like and subscribe buttons for more updates. Imagine now the USGS announcing that a previously undetected mass, an anomalous object, has begun moving slowly beneath this already tense region. The notion alone strikes a chord of wonder and unease. What could it be? A dense pocket of fluids traversing a conduit of fractured rock, perhaps? Magmatic intrusion rearranging pressure distributions deep underground? Or some unknown mass drifting invisibly along the subducting slab? Each possibility carries its own narrative. Fluids play a starring role in slow slip events, where high-pressure fluids infiltrate rock, reducing friction and unlocking silent slips along the fault interface. That object could be a plume, liquid-rich and anomalous, that is shifting into the zone where tremor and slip dance in a slow, periodic ballet. Such a movement may temporarily lubricate the interface, potentially modifying the cadence or intensity of future tremor slip cycles. Alternatively, if this is magma slowly intruding through the subducting slab, it introduces the exciting possibility of recharged volcanic systems. The Cascade Volcanic Arc, home to peaks like Mount St. Helens, Mount Hood, and Mount Rainier, lies just inland and owes its existence to these deep tectonic processes. Movement of magma or heat-producing fluids beneath the zone could signal changes in the region's volcanic dynamics. Could this be the stirrings of a nascent volcanic awakening? Or might the object be merely a dense mafic block within the descending plate, shifting, twisting into a new orientation under stress? The implications for seismic hazard are equally dramatic. The locked zone, closer to the continental edge, is where energy builds until it unleashes devastations in megathrust earthquakes. In deeper transitional zones, slow earthquakes offer a faint hint of what's happening below, as, say, a whisper before the scream. An unusual subterranean object moving through that territory could recalibrate strain fields, altering stress accumulation rates. Theoretically, slow creep or slip induced by this movement could relieve surface strain, offering a momentary reprieve. Alternatively, shifting stress could increase pressure on shallower locked zones, accelerating the onset of a catastrophic rupture similar to what happened in 1700, when a magnitude 9 earthquake shook the Pacific Northwest and sent an orphan tsunami washing into Japan. Beyond those immediate tectonic consequences, the mysterious object presents a profound scientific opportunity. If sensors, GPS, seismic arrays, and hydrophones can now observe something previously invisible, perhaps similar objects or flows exist elsewhere, waiting to be detected. This could open new frontiers in subduction zone research, revealing hidden plumbing systems, fluid reservoirs, or magmatic conduits. It might demand a rethink of how seismologists and geodesists interpret slow slip, tremor, and the conditions preceding the next great quake. Could this discovery even be a breakthrough precursor signal? If so, it might grant precious lead time to communities perched atop Cascadia's restless ground. Yet with that possibility comes caution. Unlike conventional earthquakes, which send unmistakable jolts, these subterranean signals are elusive and prone to misinterpretation. Identifying the true nature of the object, its composition, mass, motion, is no easy feat. Perhaps it's just a dense slug of basalt within the subducted plate, offsetting GPS baselines but ultimately harmless. Or it could be rapidly mobilizing fluids, signaling complex hydraulic processes at depth rather than tectonic warning. Rigorous imaging, deep drilling data, and repeated observations would be required before drawing firm conclusions. Still, the immediate reaction is human. Fascination? Concern? Urgency? In cities like Seattle, Portland, and Vancouver, where daydreams of megafires and earthquakes cast a long shadow, any hint that the ground has new secrets to share invites reflection on preparedness, resilience, and humility before Earth's deep rhythms. The object moving below suggests that the Cascadia Subduction Zone is more dynamic than once thought, its subterranean contours shifting, its pressures reshaping, its future unwritten. And so the story unfolds, anchored in tension and wonder. A strange moving presence deep in the earth beneath Cascadia, unseen by eyes above, but evident to instruments tuned to its low rumble. It occupies a place between legend and science, offering insight but demanding patience. What lies next? The tectonic narrative continues, unfolding in slow pulses and deep motions, inviting us to listen, observe, and wonder at what lies beneath, and ask, what might this mean for the tremendous forces seated along the Pacific Northwest's edge? Beneath the churning swells of the Pacific Ocean, the seafloor dips sharply toward a hidden frontier. This is where the immense weight of an oceanic plate dives beneath a continental plate, a slow-motion descent that will continue for millions of years. Now, into this already complex realm, the USGS detection of a mysterious moving object adds an entirely new layer of intrigue. The finding is not simply a point on a chart. It is a revelation that somewhere in this darkness, an unknown mass is traveling, carving its path through a geologic theater where forces beyond human scale interact. The seismic arrays that picked up the anomaly were designed to track both the violent and the subtle. Every second, they collect whispers of motion from thousands of feet below the seabed, translating them into patterns that scientists can interpret. This time, the signals were not like the usual slow tremors or microquakes. Instead, they revealed a localized, consistent, and directional movement, as though something far below was pushing steadily along a defined course. It was not noise, and it was not an error in the instruments. It was real. The anomaly began near the deeper portion of the plate interface, then tracked toward a zone that lies between the deep tremor belt and the locked portion of the subduction zone. Understanding such a motion requires knowledge of the conditions at these depths. Pressure there is almost beyond comprehension, thousands of times greater than at the surface. Temperatures rise high enough to partially melt rock, yet not uniformly so. The crust and mantle here are neither fully solid nor fully molten, but somewhere in between, forming a plastic, deformable layer. In such an environment, rock can behave like a viscous fluid over geologic time, creeping and warping under stress. If the moving object is denser than the surrounding material, it could, in theory, plow through this medium like an ancient boulder being pushed through mud. Its journey would not be silent. As it moves, it would disrupt stress fields in its vicinity, producing tiny shifts in strain detectable at the surface through precise GPS measurements. It could force fluids from one compartment to another, creating pressure imbalances. It might even generate microfractures as it passes through brittle patches, giving rise to sequences of tiny earthquakes far too deep to be felt, but easily captured by sensitive instruments. Each signal becomes a piece of a puzzle, revealing not just the presence of the object, but the nature of the material it is displacing. For researchers, this is an unprecedented opportunity to explore the hidden architecture of Cascadia. While they have long modeled the interface between plates as relatively uniform, the movement of a distinct, coherent mass challenges that assumption. It suggests a more heterogeneous environment, one with varied densities, compositions, and mechanical properties. In this view, the subduction zone is not a flat, uniform plane, but a rugged landscape with ridges, channels, pockets, and blocks that can travel great distances over deep time. The scale of the object remains uncertain, but preliminary modeling based on the amplitude and duration of the signal points to something substantial, possibly several kilometers across. If so, its influence on the surrounding zone could be profound. A migrating body of that size could alter the local geometry of the fault, potentially changing how stress is transferred between different parts of the plate boundary. This matters because earthquake rupture is highly sensitive to the geometry of the fault plane. Even small bends or irregularities can determine whether a rupture stops or propagates into a devastating megathrust event. Another layer of mystery comes from the possibility that this object has been moving for a long time, perhaps centuries, and that it has only now entered a region where the instruments can detect it clearly. Subduction is a slow process, and a mass embedded within a plate could migrate gradually, its path influenced by variations in mantle flow or by buoyancy differences between itself and the surrounding rock. If scientists could trace its trajectory backward, they might find clues in older seismic records, patterns once dismissed as noise that now take on new meaning. The potential implications extend beyond tectonics. Cascadia's subduction zone is closely tied to the Cascade range of volcanoes, which owe their existence to the melting of the subducting plate and the rise of magma through the crust. If the object is in any way related to magmatic processes, perhaps a blob of partially molten material, it could be part of a broader volcanic system that has yet to be mapped. In such a scenario, its movement could indicate shifts in magma supply, changes in melt generation, or alterations in pathways that feed the volcanoes further inland. Marine geologists are also intrigued by what this means for the seafloor above. The object's movement could be subtly warping the surface topography, raising or lowering the seabed by millimeters or even centimeters over time. Such deformations could influence deep-sea ecosystems, submarine landslides, and the stability of methane hydrate deposits that lie frozen in sediments. In extreme cases, destabilization of these hydrates could release methane into the ocean and atmosphere, with climate implications on a timescale that, while slower than tectonic shifts, is still significant. The detection of the object is also a technological triumph. Instruments along Cascadia's margin are part of an extensive observational network, including seafloor pressure sensors, ocean bottom seismometers, and satellite-based GPS. The combination of these tools allows for a three-dimensional picture of what is happening deep below. This detection showcases just how fine-tuned the system has become. In earlier decades, such a motion would have been invisible. The improvement is not merely incremental, it is transformative, giving scientists a new way to see and interpret Earth's inner workings. Yet, there remains an undercurrent of tension in the scientific community. While the discovery is exciting, it also raises questions that cannot yet be answered. Could this moving object, by altering local stress fields, influence the timing or magnitude of future seismic events? Could it interact with the deep tremor and slip cycles that have been documented in Cascadia, perhaps amplifying or dampening their effects? If it passes into the locked portion of the fault, could it serve as a nucleation point for rupture, or would it instead relieve stress harmlessly? The uncertainty fuels a sense of urgency for further investigation. Plans are already being discussed for deploying temporary seismic arrays in targeted locations, increasing the density of sensors to better track the object's motion. There is talk of using advanced seismic imaging techniques, similar to medical ultrasound but on a planetary scale, to resolve its shape and composition. Some even suggest that deep ocean drilling, although immensely challenging and costly, could provide direct samples from the surrounding material, offering definitive answers. As it moves, the object may also help calibrate the models used to predict earthquake behavior in subduction zones. Most existing models treat deep movement as either distributed creep or discrete slip events, but this is something different. A coherent translation of mass. Including such dynamics in simulations could yield more accurate forecasts of how stress accumulates and is released, not just in Cascadia, but in subduction zones worldwide. If similar moving bodies exist beneath other margins, they might explain puzzling variations in earthquake recurrence intervals and magnitudes. The public, hearing about a mysterious object beneath the subduction zone, may imagine science fiction scenarios, a colossal machine, an ancient artifact, a living creature. While the reality is firmly rooted in geology and physics, the truth is no less fascinating. The Earth's interior is an alien world, and in this case, an object the size of a mountain may be making a journey through it, unseen except by the instruments that translate its passage into patterns of data. The fact that such a thing exists, and that it is moving now, underscores how little we truly know about the dynamic planet we inhabit. The ocean above gives no hint of the drama unfolding below. Waves roll toward the shore, tides ebb and flow, and life continues much as it has for millennia. Yet in the darkness far beneath, this object continues its slow, deliberate path. Its movement is a reminder that the forces shaping our world are in constant motion, often in ways too subtle or too deep to sense without the aid of technology. Whether this journey will end in silence or in some dramatic rearrangement of the tectonic stage is a question that will only be answered with time. If the movement continues long enough for researchers to map its full trajectory, they might learn whether it is heading toward a structural boundary within the fault, toward a zone of high seismic coupling, or toward a region of known slow slip. Any of these could yield critical insights into the mechanics of subduction. And if the object eventually slows or stops, the location of its resting place could offer clues to the forces that guided it, perhaps a pocket of lower density material acting as a trap, or a bend in the subduction interface that prevents further progress. For now, the most remarkable aspect of the discovery is the way it reframes our understanding of the subduction process. No longer can we think of it solely in terms of broad, gradual movements punctuated by occasional earthquakes. Instead, we must envision a far more complex interplay, with individual masses, fluids, and perhaps partially molten zones moving independently within the larger system. Each of these components could influence the others, creating a dynamic tapestry of interactions that drive the evolution of the margin over time. The USGS detection has opened a window into this hidden realm, one that will likely inspire new research for years to come. It is a discovery that blends precision measurement with the raw, ungovernable forces of geology, a reminder that even in an age of satellites and supercomputers, the Earth retains the capacity to surprise us. Somewhere beneath the cold Pacific, an object is moving. Its journey is reshaping the deep structure of Cascadia, rewriting what we thought we knew about one of the most dangerous geological settings on the planet. And for now, all we can do is watch, measure, and try to understand the story it is telling through its steady, silent motion. One line of inquiry emerging from this discovery focuses on the possibility that the object represents a segment of oceanic crust that has resisted full assimilation into the subducting slab. In this interpretation, the anomaly could be a fragment of a seamount, a long submerged volcanic mountain that was carried toward the trench and drawn beneath the continental margin. Seamounts are not uncommon along oceanic plates, and when they reach a subduction zone, their topographic bulk can deform the overriding plate, influence fault behavior, and even generate unique seismic patterns. If this object is indeed such a remnant, its path would be defined not by the smooth glide of surrounding crust, but by the complex frictional interactions between its rugged surface and the material above and below it. A migrating seamount beneath the Cascadia interface could exert extraordinary local pressures, acting as a moving stress concentrator. This in turn could affect how the interface responds to the plate's overall motion, potentially creating localized patches of enhanced locking where strain builds more quickly than in adjacent regions. In contrast, it might also cause microfailures in surrounding rock, producing swarms of small quakes or tremor sequences that ripple outward in distinctive patterns. Seismologists tracking such variations could use them as a kind of tracer, mapping the object's influence in real time as it advances. Another possibility involves the concept of a density anomaly within the slab's mantle lithosphere. Compositional variations in oceanic plates, such as eclogite-rich zones formed from metamorphosed basalt, can create gravitational instabilities. Over long timescales, these denser regions may sink relative to their surroundings, dragging connected material with them. In a subduction setting, such a descending block might follow a trajectory influenced both by the slab's overall motion and by convection currents in the surrounding mantle. The result could be an oblique or even curving path, one that reveals far more about mantle flow patterns than surface observations ever could. If researchers can track the object over months or years, its movement could serve as a natural probe of deep Earth rheology. Every deflection in its path, every acceleration or slowdown would be a data point indicating how forces are distributed within the subduction zone. This, in turn, could refine models of how stresses migrate through the fault system, a refinement crucial for predicting the timing and scale of future tectonic events. The object is more than a curiosity. It is a messenger from the inaccessible depths, carrying with it a record of the pressures, temperatures, and materials it encounters, and offering the scientific community an unprecedented chance to read the hidden language of Cascadia's interior. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the USGS detecting this object? What do you expect happens? We want to hear from you. Thank you for watching, and see you